Hey guys, welcome back to another Chem 104 lecture. In this lecture video, we are going to talk about aromatic compounds. More specifically, we are going to talk about benzene ring as the aromatic compound. There's many aromatic compounds out there in organic chemistry. Some aromatic compounds are much more complex than benzene, and some aromatic compounds are much more simpler than benzene. And so in the two structures that you guys see on the screen, these are two examples of aromatic compounds. One is vanillin and one is acetaminophen. And so if you look at both of these compounds, what they have in common is that ring that you guys see in the middle. It's very prominent. And so I'm referring to this ring. And so this ring is known as a benzene ring. And I'll talk more about benzene rings in just a few, but I do want to give you guys a couple of real-life examples of aromatic compounds. And so if you guys are a home baker, and if you like to make vanilla cupcakes or vanilla ice cream, and you like to do it from scratch, that means, taking the actual vanilla bean and then opening it up, scraping the bean off, and immersing what you're trying to cook with it, with the bean. The active ingredient that attributes to the smell of vanilla and the taste of vanilla is vanillin. And so here for vanillin, we have this aromatic compound that's basically right in the middle. So this is a benzene ring. And then surrounding this benzene ring are substituents, functional groups that we'll talk about in a future lecture video, such as an aldehyde. That's the one that I just circled in pink. And then here we've already come across this functional group. This is a hydroxyl functional group, the OH. And then last but not least, we have this OCH3. This is going to be an ether. And so vanillin, what produces the properties of vanillin is a combination of all three of these functional groups in pink attached to that benzene ring that I circled in green. And so acetaminophen, this is the active component, active ingredient in Tylenol. So if you guys are out there buying Tylenol, if you guys are looking at the box, it says acetaminophen. This is the structure, the organic structure of acetaminophen. And hopefully with your current knowledge of organic chemistry and the skeletal structure, you can imagine all of the invisible hydrogens or the missing hydrogens that's been excluded from this skeletal structure. And so once again, we have this benzene ring that's right in the middle. Then we have that alcohol group, that hydroxyl group, very similar to vanillin. Here we have an amide. And so this is a functional group that we're going to discuss later on. Now, if you guys look at the name of this molecule, acetaminophen, and there's no way that, well, maybe some of you guys know this, but if you guys kind of break down its word, so acet is short for the acetyl group, and so the acetyl group is this portion right here in acetaminophen, and then amino is that nitrogenous functional group. And so if you guys took biology before this class, hopefully you guys are familiar with this amino functional group. And then fen is going to be, it's shortened from the word phenol. And we're going to discuss phenols in this lecture video a little bit later. And so the word acetaminophen stems from, the main composition of this of the organic structure. So we have a phenol, we have an amino group, and we have an acetyl group. So combined, we get acetaminophen. Now, that's one way to name a new drug. There's definitely an IUPAC name for acetaminophen. Acetaminophen is just a common name. All right, let's go ahead and talk about the details of aromatic compounds. And so, like what I mentioned earlier, the only aromatic compound that we're going to be focusing on today's lecture is going to be benzene. The rest of the aromatic compounds is for the full year of organic chemistry. And so, looking at the expanded structure of benzene, notice that here we have the chemical formula for benzene. And so the expanded structure of benzene shows us that it's composed of 6 carbons. And then in each of those carbons, there are 1, 2, 3, 4, 5, 6 hydrogens, giving us the chemical formula that we see at the bottom. Now, if we were to translate this expanded structure of benzene into a skeletal structure, this is the skeletal structure that we would get. And so just be very mindful that all of the hydrogens have been excluded and all the carbons are represented as corners or vertices where the two lines just kind of meet and intersect. And so whenever you guys are looking at the structure, automatically in your mind, you should know that there's one hydrogen here, there's another hydrogen here, there's another hydrogen here, and so forth and so forth. So please remember that each carbon in your organic molecule must follow the octet rule. And so if it currently has 3 covalent bonds, then it's just missing one more covalent bond, which is probably filled in by a hydrogen. Now, the really cool thing about aromatic compounds is that they have this characteristic feature to them. It's called conjugation, specifically conjugation of the bonding pattern. So here we have a double bond. Maybe I'll do this in a different color. So here we have a double bond. And then if we go to the right or left of it, then it's going to be a single bond. And then moving on to the next carbon, next pair of carbons, we have a double bond again, then a single, double, single. So you have this conjugation of double, single, double, single, double, single, and that's very characteristic for a lot of these aromatic compounds. And so if you wanted to determine if a compound is aromatic, just generally speaking, you can apply Haeckel's rule, which again is dedicated for the full year of organic chemistry, but I just decided to toss that up if you were curious. All right, so now that we've determined, now that we've seen the skeletal structure and the expanded structure of benzene, we're going to go ahead and look at its three-dimensional character. And so if you are looking at this ball and stick model, this ball and stick model is telling you that the bond angle is going to be 120 degrees. And so 120 degrees is referring to the fact that its electron geometry is going to be trigonal planar. And when your electron geometry is trigonal planar, you know that it's going to be a flat molecule. So how do I know this molecule is trigonal planar? Well, I have 1, 2, 3 groups of electrons surrounding the central atom, right? So that's from general chemistry. Now, if you look here, I have 1, 2, 3 groups of electrons surrounding this carbon. So this carbon is also trigonal planar. Oops. Now, if you guys are looking at this carbon, once again, I have 1, 2, 3 groups of electrons. So it's trigonal planar. if you guys are looking at this carbon, it's also trigonal planar because it has 1, 2, 3 groups of electrons. And so you guys can kind of repeat that exercise in your mind, but long story short, every single carbon on a benzene ring has an electron geometry that's trigonal planar, which emphasizes that this molecule is completely flat. And so just imagine you looking at the edge of your paper. Nothing is going to be above the paper, nothing is below the paper, right? And so going back to the the expanded structure of benzene, notice that every single one of these bonds are either carbon-carbon or carbon-hydrogen. And so therefore, the polarity of those bonds are non-polar covalent. Okay. So if you recall, covalent means to share electrons, and non-polar means that it's shared equally. So it's a non-polar covalent bond. Now, if you guys are looking at the entire molecule as a whole, a benzene ring is primarily composed of carbons and hydrogens. And so this molecule, very similar to alkenes, alkynes, and alkanes, without the halide substituents and all of that stuff, these are non-polar compounds. So overall, the molecule is non-polar, meaning that if you were to mix it with water, you should see a separation between the two. So you'll have a top layer that's going to be benzene, and then you'll have a bottom layer that's going to be water. So you form a heterogeneous solution. All right, so this is just summarizing what I had just mentioned. The carbon is trigonal planar. Each carbon is trigonal planar, making the whole entire benzene a planar molecule, so it's flat. And that has some strong biological effects. And so, for example, if you're thinking about the cellular membrane, the cellular membrane itself is going to be non-polar. And so having these planar molecules allows these aromatic compounds to kind of embed itself very nicely inside the non-polar layer of a phospholipid. And so, you know, some steroids, if you will, can help stabilize the fluidity of cell membranes under different temperatures. I'm trying not to get into that topic just because it's out of scope for this class. And so hopefully you guys discuss things like that in your biochemistry or your biology class. But long story short, I do make such a big deal about electron geometry and, you know, whether or not it's flat or three-dimensional. One, so that we can depict it correctly on paper. And number two, there are some biological, it gives, you know, specific properties of that drug or molecule in a biological or biochemical aspect. So the next item that I want to discuss is resonance. And so resonance is one of these terms that you guys are going to come across in higher levels of chemistry or organic chemistry, or even biochemistry. And so resonance describes the delocalization of electrons. So delocalization of electrons. So what does it mean? Well, let's go ahead and cross out D for now, localization, right? And so if electrons are localized, then that means it stays within the carbons that we're currently seeing. And so if this bond, if this double bond, if the electrons on the double bond is localized, then that means it's just going to stay where it's seen and drawn. It's not going to go anywhere. Now, for aromatic compounds, one of their properties is this idea of delocalization of electrons, where the electrons that make up the double bond are in constant motion. And we didn't go over this in general chemistry, in the general chemistry portion of this course, just because it's a little bit out of scope for this class. But there's things called pi bonds, and pi bonds are where the electrons that create the double bonds are located. And so, long story short, these electrons can delocalize if they're in this conjugated manner, where you have a double, single, double, single, double, single pattern. Okay. And so, if an electron, if a pair of electrons were to delocalize, then it would move just one space over. It would just kind of jump from one carbon to another. And since we have to maintain the correct number of bonds for each carbon, having one pair of electron delocalize, in other words, jumping to the next carbon, is going to force this bond to also move. And consequently, it will force this bond to move, because we want to make sure that the number of covalent bonds on each carbon, it follows the octet rule. Okay? And so I'm just going to go ahead and quickly show you. So remember that there's a hydrogen here. There's also a hydrogen here. And there's also an invisible hydrogen here. So if this double bond were to move this way and the other double bonds don't move at all, then we'll get a bond that looks like this. Now, this carbon, if you count it, it already has 1, 2, 3. And then if you don't move the other double bond, it'll have 4 and 5 bonds on this carbon. And you can't have carbon with 5 bonds, because now it's destroying the octet rule. And so to ensure that the octet rule, to ensure that the carbon is still stable, when this double bond, I'm going to change my color again, when this double bond moves, so when this pair of electrons from this double bond moves or is delocalized, the pair of electrons that's found in this double bond also needs to move to the next carbon over, and the same thing here. And so what we get is, I'm going to draw the result. So what we get is a structure that looks like this. So hopefully you guys can see that. You can see the differences between the two. We didn't really change the number of hydrogens. The number of hydrogens for each carbon is still 1, 1, 1, 1, 1, 1, 1. The only thing that we changed is the position of those electrons that created that double bond. And once again, if we were to delocalize, these electrons that form the double bond, we get a structure that's very similar to the original structure. Okay. And so because we can go forwards and backwards between both of these structures, this is telling us that these structures are equivalent to each other. And if we take if we hybridize, if we overlap, if you will. Okay, so I'll go ahead and just show you. If I take this and if I overlap it with the original structure, notice how it kind of forms a ring within a ring. Okay, and so when I overlap those two compounds, I can go ahead and write a hybrid structure. I'm not going to draw this. I'm just going to copy and paste. I'm going to cheat just a little bit. Okay. I'm going to draw a hybrid structure that's a composition of both of these two. Okay. Ooh, wow, that's actually really good. And so notice that we just get a ring within a ring. And so we can go ahead and summarize this. You don't have to draw this all fancy, but we can go ahead and summarize all of this by putting a ring inside our cyclohexane, okay, our hexagon. And so overall that ring is telling or communicating to the reader that you have a delocalization of these electrons. And so this is known as the hybrid structure of a benzene ring. And so this slide just demonstrates what I've talked about in the previous slide. And so the main idea is that all three of these representations of benzene are equivalent. And you guys can use one or the other. It doesn't really matter. Finally, this delocalization of benzene provides added stability compared to unsaturated carbons, unsaturated hydrocarbons. And this is observed when we're talking about our chemical reactions such as hydration and hydrogenation. So I'm going to skip graphene for now. I'm just going to jump to the slide here. So typically aromatic compounds, because of resonance, this added stability, they don't undergo addition reaction, unlike alkenes. So alkenes undergo addition reaction. And so if you guys recall, there are two different types of addition reactions that we discussed in the previous lecture video. One of them was H2 and palladium, which is hydrogenation. And if you guys recall, the hydrogenation just produces an alkane. Whereas if you have hydration, water and sulfuric acid, you guys are going to obtain an alcohol. Okay. And so both of these addition products, or both of these addition reactions, happen for alkenes with no conjugation. So alkenes that are not considered aromatic, they are more susceptible to these types of reactions just because they're not as stable compared to something like benzene. Okay? And so if you were to perform, for example, if you were to mix hydrogen gas and palladium, no reaction will occur. In other words, the benzene will still be benzene and hydrogen will still be hydrogen. Okay? The same is true for, the hydration reaction. So if you have a hydration reaction with benzene, then once again, no product will be formed or no reaction will occur. The product that is formed is the same as the reactant. So once again, benzene will be benzene, water will be water, and that's your product basically, right? No reaction, no addition product. All right. And so it's important for us to understand that benzenes have this this resonance structure to it, and the resonance structure gives it that extra stability so that it's not susceptible to undergoing addition reactions. Okay. All right, and so let's go ahead and talk about naming these aromatic compounds. And when we're naming these aromatic compounds, we're only dealing with benzene. So we're going to learn how to name benzene rings with either one substituent or many substituents. And so let's go ahead and look at benzene rings with one substituent. And so if you guys only have one substituent to it, the carbon that has that substituent is always going to be carbon number 1. It's very similar to what I've discussed when we were talking about cycloalkanes. And so for cycloalkanes, if you only have one substituent, the carbon that substituent is attached to is automatically carbon 1. So we don't need to communicate that to the reader. It's already implied. And so if you guys are looking at the names, you don't see like one ethyl, one butyl, or anything like that. With one substituent, you just name the substituent, and then you add the word benzene at the very end. So here, if I look at this example, this is my benzene ring, and 2-carbon compound is an ethyl. So a 2-carbon substituent is an ethyl. And so when you put these two names together, it's just ethyl benzene with no space. If you guys are looking at the next example on the right, once again we see the benzene ring, and we see a 1, 2, 3, 4 carbon substituent. So that's a butyl. And so that butyl was derived from butane. And since it's a substituent, you drop the ANE and you add the YL. So that's why it's called butyl. And so once you guys have identified your substituent, you just write the substituent first. You name the substituent first, and then you're going to add the word benzene at the very end to represent that benzene is the parent compound of that structure. Same idea here, chlorobenzene. And so in all scenarios, the carbon that I'm kind of identifying in blue, that's automatically carbon number 1. Because you only have one substituent, there's no reason for us to add that number 1 in our naming, in the name of the compound. Now, some monosubstituted benzenes have common names. And sometimes you guys will use these common names to take place of the word benzene. And so if you guys have a benzene ring with one CH3 or a methyl group, this is known as methylbenzene, or that's the common name, right? Methylbenzene. Now the common name that you guys are going to use is toluene. So you need to memorize or be very familiar that if you have a benzene ring, with a methyl group that looks like this is going to be toluene. Now remember that this methyl group doesn't have to point to the right. You can literally rotate it anywhere. Okay, and the same holds true for all of these other common benzenes, monosubstituted benzenes. And so if you have a benzene with a hydroxyl group, this is known as a phenol, right? So remember acetaminophen. So I'm going to scroll all the way up. So acetaminophen was the main component in Tylenol. And so this benzene ring with the hydroxyl group, that is your phenol. And so that's going to be representing the parent name for the compound. Okay. So last but not least, here we have aniline. So aniline, it's when you have an NH2 or some derivative of NH. Well, let's just keep it NH2 for now. Attached to the benzene ring. So the formal name is aminobenzene, but the common name is aniline. The formal name is hydroxybenzene, but the common name is phenol. The formal name is methylbenzene for toluene, but toluene is the common name. And so when you guys have a polysubstituted benzene, you might, and if it has one of these structures like toluene, phenol, aniline, you guys are going to utilize the name of these structures when you're naming polysubstituted benzene. And we'll go through some examples. Also, carbon 1 is on the substituent. So for example, if you're saying toluene, this is automatically carbon 1. This is automatically, this right here is automatically carbon 1. And finally, this guy right here is automatically number 1, carbon number 1. Okay. So that really helps us when we're naming polysubstituted benzenes in terms of trying to figure out where carbon number 1 is. We just got to figure out if it rotates, if the numbering system is going to go clockwise or counterclockwise. All right, so let's talk about naming polysubstituted benzenes. So generally the pattern for naming these polysubstituted benzenes, they're very similar to what we've done for cycloalkanes, for alkanes, alkenes, alkynes, the list goes on. However, there are just some reminders, maybe some subtle differences between the two. So let's go ahead and go through these rules or these reminders. And so we just want to make sure that the carbons, we're going to number the carbons such that the substituents gets the lowest possible number. Okay. And then when we name our compound or organic or aromatic compound, we're going to alphabetize the substituent name. So it goes in alphabetical order. Okay, A, B, C, D, etc. Now, some subtle differences between naming polysubstituted benzenes and that of like alkenes, alkanes, alkynes is substituents that are part of the common root. So for example, if you had aniline, toluene, and phenol, you're going to use aniline, toluene, phenol as like the name of the parent chain. And then everything else outside of that is going to be your substituent. And so here we're going to put the common root substituent at carbon 1, but we're going to omit 1 from the name. Okay. And so if you were to say aniline, we already know that NH2 is carbon number 1, so we don't need to say 1 aniline. Okay, we just say aniline and that's it. And we'll go through some examples. Actually, let's do that right now. Okay. All right, so let's go ahead and go through this first example. Here I have a polysubstituted benzene. And I know that it's a polysubstituted benzene because I recognize that there is that conjugation double, single, double, single, double, single. So that's what makes it a benzene. And it's polysubstituted because there are more than one. Because there's more than one substituent. to the left, to the right, sorry. And so the first thing I want to ask myself is, do I have aniline, which is the NH2? Do I have toluene, which is just one CH3? Do I have a phenol, which is that OH attachment to the benzene? Okay. And so if you look at the structure, I have a chlorine, a propyl group. So this is my chlorine, my propyl, and I have an ethyl group. And so we don't have, this structure doesn't have NH2, a CH3, and an OH. And so therefore, the name of the parent is going to be benzene. Okay. And now all we have to do is just figure out what is going to be we're just going to have to figure out which one is going to be carbon number 1, carbon number 2, carbon number 3, carbon 4, etc., etc. And let's see here. We're also going to have to figure out the substituents, which we kind of already did. It's in green highlight. And then we're going to put the carbon numbers together with that of the substituents, and then just name them as we normally would. But the tricky part here for polysubstituted benzenes without your aniline, your toluene, your phenol is determining what's carbon 1, what's carbon 2, what's carbon 3, what's carbon 4, 5, etc., etc. All right, so let's go ahead and check this out. So this, we have an ethyl. Okay. So here we have a propyl. And here we have a chloro. Okay. And so what we're going to do is we are going to number this carbon system such that we're going to get the lowest number for each and every single one of these substituents. And so there's going to be many iterations of this. All right, so what we're going to do is we're just going to say that chlorine is carbon number 1. Okay. So because I don't have aniline, toluene, or phenol, I need to figure out which of these substituents is carbon number 1. And so if I arbitrarily say that chloro is carbon number 1, then if I do clockwise, and this is 2, 3, 4, 5, 6, and then that's it. And so if you look at the sum of my numbers, I have 1, 4, and 5. Okay. And so those numbers are kind of large. So let's see here. I have chlorine, such as 1. So if I do chlorine as my number 1, I get 1, 4, and 5 if I do this clockwise. Now if I do chlorine as counterclockwise, 1, 2, 3, 4, 5, 6. So if I go counterclockwise, and if I make chlorine my number 1, then I have 3 on propyl, and I have 4 on ethyl. Okay. And so it looks like chlorine 1, 3, and 4 is much more preferable than chlorine 1, 4, 5. Now that I've done the chlorine clockwise and counterclockwise, I'm going to go ahead and do the same for the other two. And so I'm going to just assume that ethyl is going to be carbon 1. And if I go clockwise, I have 1, 2, 3, 4, 5, 6. Okay. Maybe I should put in here chlorine, propyl, and then ethyl. And so if I go clockwise, making ethyl number 1, then here in this case, propyl will be number 2, and chloro will be number 4. And so I'm going to now go counterclockwise and see what numbers I get if I make ethyl carbon number 1. So 1, 2, 3, 4, 5, 6. So if I go counterclockwise with ethyl being number 1, I can see that for chloro, that's going to be on carbon 4, and propyl is going to be on carbon 6. So between the two ethyls, it looks like this is the wrong combination. Now, if I compare my chlorine to my ethyl, I want you guys to note that 1, 2, and 4, that combination is going to produce a lower number than 1, 3, and 4. And so it looks like chlorine is out of the picture being carbon number 1, because I've created a combination such that ethyl being carbon number 1, and if I number it clockwise, I get a lower combination than chlorine being numbered counterclockwise. Okay. All right, and so we have one more set to go through, which is going to be propyl. So what if my propyl was number 1? If my propyl is number 1, I'll go clockwise. So 1, 2, 3, 4, 5, 6. So I'll go ahead and put in, did I do clockwise? Yeah, I did. So clockwise with propyl being carbon number 1. If propyl clockwise is number 1, then chloro is number 3, and ethyl is number 6. So I have a combination of 1, 3, and 6. Now, if I go counterclockwise, okay, so in other words, I'm going to have 1, 2, 3, 4, 5, 6. So if I go counterclockwise with propyl as carbon number 1, my ethyl will be on carbon 2, and my chloro will be on carbon 5. Okay. So hopefully you guys see that. So here I have ethyl as carbon 2 and chloro as carbon 5, when propyl is carbon number 1, and I'm going counterclockwise. Now, let's go ahead and compare all 6 combinations. And this is just for determining the numbering for our benzene ring. Sometimes it's a little bit complicated like this, but not all the time. And so if you look, 1, 2, and 4 is going to be much lower than 1, 3, and 6. So if you add all of these numbers up, it's going to produce a higher number than 1, 2, and 4. So this guy's out of the running. So if you guys look at propyl, if we number it, if we deem propyl as carbon number 1, and if we number it counterclockwise, we get a combination of 1, 2, and 5. So 1 plus 2 plus 5 is going to be a bigger number than 1 plus 2 plus 4. We can already see the difference between 4 and 5. And so here in this case, this guy is out of the picture. Okay. So it looks like the lowest combination, the lowest possible combination for us to number our substituents so that each substituent will get the lowest possible value is going to be when ethyl is carbon number 1 and we are numbering the system clockwise. Okay. So after all of those, after listing out all of those combinations, we're going to go ahead and conclude that carbon number 1 truly is on ethyl and not on any of these other substituents. And we're going to number it clockwise. And if we number it clockwise, this gives us number 2, number 3, number 4, number 5, and number 6. And so here we have 1 ethyl, here we have 2 propyl, and then here we have 4 chloro. And that's only to determine the numbering system for this specific benzene. Okay. And so this is what happens when you guys do not have aniline, toluene, or phenol. We have to figure out what the substituent that would be referred to as carbon number 1, and to do that we have to figure out all of the different combinations of the numbering system, both clockwise and counterclockwise, assuming each substituent could be representing carbon number 1. All right, so now that that's done, we're going to figure out what we're going to name first, second, third, and fourth. And this is done by alphabetical order. And so for chloro, so notice how 4-chloro starts with C. So this is the first substituent that we're going to name. The second substituent that we're going to name is probably ethyl because it starts with the letter E. And then the third is going to be the propyl. The P comes very later in the alphabet. And then once we have all of the substituents named, we're going to go ahead and add in benzene. And so I'm going to go ahead and move this stuff over to the right just so I have room to write my final answer without it being too crowded. All right, so I'm going to put in 4-chloro. Number 2 is 1-ethyl. Number 3 is 2-propyl. And number 4 is going to be benzene. Benzene is always last because that is the parent. All of your substituents needs to be numbered alphabetically. Or or it's going to be organized in alphabetical order. And the numbering system is independent of, the letters. It's independent of the fact that, chlorine starts with C and it's the closest thing to the very start of the alphabet. Anyways, so to finish this up, we just need to fix our grammar, so to speak. We've got to make sure that our punctuations are correct. And so letter to number, I need a dash. Letter to number, I need a dash. Letter to letter, I don't need a dash. I don't need a comma. I'm going to stick this guy and put it close to propyl. And so my punctuation, I don't know why I'm saying grammar. So all of the little nitty-gritty details for naming this organic compound is now done. So we have all of the dashes, commas, and spaces accounted for. So once again, the numbering of the carbon is just always so important, and that's typically where a lot of students struggle. And so the rules are a little bit different for aromatic compounds compared to alkanes, alkenes, and alkynes. And so the only way that for you guys to kind of like master this is to keep on doing problems. I posted a whole bunch of worksheets on your Canvas. And so feel free to open those documents and kind of go through them. I believe those worksheets have answers. Also, you can open up the PowerPoint and just kind of go through those structures that I've posted and really try to understand how to number the carbon system if it's an alkane, number the carbon system if it's an alkene, number the carbons if it's an alkyne or aromatic. All right, so let's go ahead and move on to the next problem. And so I'm going to go ahead and copy and paste this question. So whenever we're working with aromatics, I need to ask myself, do I have an aniline, which is an NH2? It's going to be the substituent that's going to be on the benzene ring. So aniline is not NH2. I'm just saying that there's a benzene ring with an NH2 forming aniline. I'm just shortening it up. So if there's a CH3 on a benzene ring, then we'll have toluene. If there's an OH on a benzene ring, then we'll have a phenol. And so if you look at the structure that I've presented, we do have an NH2. We do have aniline. And so since we have aniline, it actually makes our job very easy because we now know that this is automatically carbon number 1. We don't really have to go through all those intense hoops like what we did for this compound where I had to list all the possible combination if I go clockwise or counterclockwise for every single substituent just to see which combination would give me the lowest values. Since I have aniline as since I have NH2 on my benzene ring, automatically my parent is going to be everything that I'm highlighting in green. Okay. And so the name of my parent ring is going to be aniline and not, benzene. And so now I just have to figure out whether or not to go clockwise or counterclockwise. Okay. So I still have to do that, but at least I know that NH2 is going to represent carbon number 1 on this benzene ring. And so if I, let's do counterclockwise. If I go counterclockwise, then this is going to be carbon number 2, carbon number 3, carbon number 4, carbon number 5, and then carbon number 6. And so we're going to take NH2 as our reference point, and that's going to be carbon number 1. And so chlorine, if we go clockwise, that's going to be carbon number 2. The other chlorine is going to be carbon number 4. So we have a combination of 1, 2, 4. If we go counterclockwise, not clockwise. Okay. And we're going to go ahead and repeat this same procedure, but now we're going to go clockwise. So this is going to be carbon number 2, 3, 4, 5, and 6. And so if we go clockwise with NH2 as our reference point for it being carbon number 1, then, here if we kind of go counterclockwise, or is this clockwise? Oh, it is clockwise. Whoops. Too late in the night. All right, so the previous one was counterclockwise. Yeah, and this one is clockwise. Okay. I think I drew the signs right, but I just said it wrong. Anyways, and so here in this case, if we go clockwise, then carbon 4 is going to represent chlorine, and carbon 6 is going to represent the other chlorine. And automatically you can already tell that 146, that set, is going to be much higher. It's going to, and when you add all those numbers up, it's going to be much higher than if you add 1, 2, and 4 together. And so it looks like the numbering of my benzene ring has to go counterclockwise. Such that this is number 1, number 2, number 3, number 4, number 5, and number 6. Okay, counterclockwise. Did I say that? I think I did. Oh man, 11:30. All right, so let's go ahead and name my substituents. So here I have 2-chloro. Here I have 4-chloro. And that's it. And so since I have chloro, I need to put them together and say 2,4-dichloro. And the parent name is going to be aniline. And that is the name of this organic compound. So this second example isn't as bad as the first, just because we have that NH2 present, making us having that NH2 present does two things. It already sets the tone, the precedence, I suppose, that that carbon where the NH2 is found is carbon number 1. And so we just need to figure out if we're going to go if we're going to number it clockwise or counterclockwise. Okay. All right, let's go ahead and look at another example. And so I'm going to go ahead and paste this here just to remind us. So do I have an NH2CH3 or OH as one of my substituents? And if you look at the top, I do. Okay, actually I should do pink. I always do pink for parent. So I do have my OH present, so therefore the name of the parent is phenol. And the phenol is describing everything here. Okay, so that whole thing in pink is a phenol. So that leaves me to figure out my numbering system. And so this carbon, where that OH is found on the phenol, is carbon 1. So it's very similar to aniline. I just need to figure out if I'm going to go clockwise or counterclockwise in my numbering. Okay? And we have to look at both situations, unless you guys can already see it. And so let's go ahead and do counterclockwise. Got to make sure I say it right. All right, so if I do counterclockwise, and this is going to be 2, 3, 4, 5, and 6. And so if I look at the carbon number in which my substituents are located, I'm going to go ahead and highlight this in green. I always highlight my substituents green. I don't know why I changed it in the previous example. I just kind of forgot. Then my numbering system, if I go counterclockwise, is going to be 1, 4, and 5. So now that I have my numbering system, if I go counterclockwise, I'm going to go ahead and redo it again if I were to go clockwise. So 1, 2, 3, 4, 5, 6. Okay. And so it looks like if I go clockwise, I have a substituent on carbon 1, I have another substituent on carbon 3, and I have another substituent on carbon 4. So if you were just to compare these numbers, you can automatically see that this set, if you add them, will give you a higher value. And so if you were to add this set, it would produce a lower value than if you were to go counterclockwise. So this is telling me that this is the correct numbering system for this organic compound, for this aromatic compound. And now that I have my numbering system in place, I'm just going to go ahead and describe this substituent. So this is going to be 3-chloro. This is going to be 4-bromo. And now that I have described the substituent correctly with respect to their carbon number on the parent chain, the only thing I need to do is combine all these pieces together to create my final answer. And so since B comes before C, the 4-bromo substituent will be named first. Next is going to be the 3-chloro. Then last but not least, it's the parent name phenol. And just to make sure that I have everything correct, I'm going from letter to number. So I need a dash. Letter to letter, that means I need to kind of scoot them close to each other so that just forms one word. I'm going to go ahead and erase my arrows, and I have my final answer. 4-bromo 3-chlorophenol. Cool. So I believe I have a couple more examples. Yeah, just 2 more examples. All right. So once again, for these aromatic compounds, these polysubstituted benzene rings, I'm going to ask myself, do I have an NH2, a CH3, or OH present in my benzene molecule? And I do. So I have this OH making this, making the name of the parent chain phenol. And so that's going to be representative of everything I'm highlighting in pink. And everything else that's not highlighted in pink, it's going to be green, which is going to be my substituent. And so I'm going to go ahead and put this as my parent. That's the parent name. All right, so next I have to figure out my numbering system. So because I have the OH in the phenol, wherever that OH is, that's automatically carbon number 1. And so now I just need to figure out if I'm going to go from left to right. Or I'm sorry, if I'm going to go, counterclockwise or clockwise. And so if I go counterclockwise, then this is going to be number 2, number 3, 4, 5, 6. So it looks like I have a substituent in carbon 3 and carbon 5. Now let's go ahead and do the opposite direction. So we're going to go clockwise. 2, 3, 4, 5, 6. Now it looks like on it looks like carbon 3, if I go clockwise, if I go clockwise, it looks like I have a substituent in carbon 3 and 5 as well. So since both of them work, and since both of them are the same substituent, we're just going to go ahead and, it really doesn't matter, it's symmetrical. So both of them are equivalent. And both of the substituents are the same, so it's symmetrical. And so we're going to go ahead and describe this as 3-bromo. And I'm going to describe this as 5-bromo. And so since I have 2 bromines, I'm going to go ahead and combine them together to have 3,5-dibromo. Did I say dibromo? Did I say di? Oh, I did say dichloro. Good. So since I have 2 bromines, I'm going to go ahead and put in 3,5-dibromo. And after that, I'm going to describe the parent, which is phenol. So 3,5-dibromo phenol. Cool. So let's go ahead and do one last one. This one's kind of a doozy. So we have our last aromatic compound that I want to cover or go over. And so I'm going to ask myself, do I have an H2? No, I don't. Do I see a CH3? No, I don't. Do I see a phenol or an OH? No, I don't. And so since I don't have any of this, the name of my parent, it's going to be benzene. So this is very similar to our first example, where we really do have to figure out what substituent is going to be considered carbon number 1. And so that means that I have to go clockwise and counterclockwise and look at the combination of numbers that they produce for each substituent. Sounds kind of nasty. So let's go ahead and do it. So this is going to be, in pink, is going to be the parent, and my parent is benzene. So my substituent is everything in green. So I'm going to just make an assumption that this ethyl is going to be carbon 1. And so what if my numbering system goes clockwise with ethyl as carbon 1? And so if I go clockwise, and this is 2, 3, 4, 5, 6. Okay. So that means I have a substituent on 2, 3, and 5. So 1, 2, 3, and 5. All right. So what if I go counterclockwise? What would I get? So I get 1, 2, 3, 4, 5, 6. And so if I go counterclockwise, with respect to ethyl, then I have 1, 3, 5, and 6. So between the two, which one will have a lower set? So the top one will have a lower set. So the counterclockwise version is incorrect. So now I'm going to go ahead and look at chlorine. So I'm going to repeat the same procedure, and I'm going to assume the carbon that has chlorine is going to be carbon 1. I'm going to go clockwise and counterclockwise if my chlorine, or clockwise and counterclockwise with respect to chlorine. And so if I go clockwise, so this is 2, 3, 4, 5, 6, I have a substituent on 1, 2, 4, and 6. So if we compare that to ethyl, oh, sorry, wrong place. Okay. So if we compare that to ethyl, I already see a higher number here and here. So this is probably the incorrect numbering system. So now I'm going to do it for when it's numbered counterclockwise. So this is going to be 1, 2, 3, 4, 5, and 6. And so for if chlorine is number 1, then ethyl is going to be number 2, bromine is 4, and the other bromine is 6. And so if I go counterclockwise, it looks like I get a higher set. And that is this combination that I just crossed out is lower than this set that we originally had. Okay. All right, so we're going to go ahead and erase that and continue on with the next substituent. So let's just say that we're going to make bromine carbon number 1. So if bromine is carbon number 1, then I can go clockwise or counterclockwise. And so if I do clockwise, that's 1, 2, 3, 4, 5, 6. I have 1, 3, 5, and 6. Does 1, 3, 5, 6 beat 1, 2, 3, 5? No, it doesn't. So this is 1, 3, 5, and 6 if I go clockwise. And so I have higher values down here at the bottom than what I have here on the top. So that one's wrong. So this is not the correct numbering system. Now I have to do the same thing for counterclockwise. So here I have 1, 2, 3, 4, 5, and 6. And so if I do that, let's see here, I'll have bromine 1, the chlorine on top is 2, the ethyl is going to be 3, and the bromine is going to be 5. All right. And so if you look at the combination, I have 1, 2, 3, 5. I also have 1, 2, 3, 5. So I have equivalent numbering systems. Okay. And so we're going to go ahead and look at the second bromine. So we're going to do one more set of combinations. Okay. So for the second bromine, this bromine right here, if we're going to go clockwise and counterclockwise for the second bromine, let's see what we get. So this is number 1. If I go clockwise, this is 2, 3, 4, 5, 6. So I have substituents on 1, 3, 4, and 5. So already the set is higher than these two that's on the right. So if I erase all of that, and then if I'm still making this bromine number 1, if I go counterclockwise, I have 1, 2, 3, 4, 5, and 6. And so here in this case, let's see here. I have bromine on carbon 1, 3, 4, and 5. And so these sets is going to be higher than these guys. And therefore, this is incorrect. And so it looks like we have two options. We have this numbering system and this numbering system. And so we're going to ask ourselves which numbering system we're going to use. And so it turns out that in this scenario, we're going to go ahead and choose the numbering system based on alphabetical order. And so B comes before E. And so we're going to go ahead and use this numbering system. And so the bromine, the first bromine that we see, that's going to be carbon 1, and we're going to number it counterclockwise. So this is 2, 3, 4, 5, and 6. And so I'm going to go ahead and now describe everything. So I have 1 bromo, 2 chloro, 3 ethyl, and 5 bromo. All right. And so what we're going to do is we're going to just combine all of these numbers, all of these parts, and we're going to do this alphabetically. So B comes first, so we have to combine both of these two, then chloro, then ethyl, and then benzene. And so the final name for this is just going to be 1,5-dibromo. Then 2-chloro, 3-ethyl, benzene. Okay. So I name both of these first, then second, then third, then fourth. For the substituents, make sure they're just in alphabetical order, B, C, E. And then your parent is always going to be the last thing that you name. All right, so that's pretty much it for this chapter. This covers the entirety of chapter 11. Lots of videos, lots of material to cover. And we're going to move on to chapter 12. I'll see you guys sometime in the near future. Bye.